Hey everyone, how are we doing? Make sure we're done with me. We're done with the music. Yay! I thought the music was going. Tiffany, we got some problems here. Let's check it out. Hi, Pros Brian. When you have a time, can you please take a look at the email I sent you? I do not want to. Yeah, I saw that. I emailed you back. Let's see. I was doing that between classes. Had 2 meetings, so yay! Also on chapter 13, several factors, including creation of comfortable when the sample size is comfortable. Yes. I think that's the true false one, right? Let's do that here in a second. Can you check a problem, a philanthropic organization? Here, we'll check that to start. Let's hop into this. Let me get the grades off the screen. Let's go right here. Da-da-da-da. There's a thing with my Pearson. My Pearson, 2 seconds, Tiffany. My Pearson is driving me absolutely nuts. I do not know if it's not saving this setting for one class. I've been trying to fix this all day with my Pearson with section 4 because people have been saying they can't access it. And I have no idea. It keeps blocking it on me. Okay, no, it should be open now. I believe it is open now. Can you send me a screenshot? What do you see? There was an issue earlier and then it wasn't saving it. My Pearson was acting weird with me. So I'm looking at the mathematics. 2.57. Let me see your mathematics right here. 2.7. That looks accurate. Yeah, it looks accurate, Tiffany. But something looks to have gone wrong maybe on the mathematics. I think there was a decimal carrying issue. So let me grab your email, Tiffany, right here, and we'll take a look at this. And let's take a look. Okay. Or let me take the problem. We'll go through this problem here and take a look at it. Alright, here we go. Let's take a look. Hey, Kayla, what's up? How are you today, Kayla? I'm doing great. Let's take a look at this on the main screen here. Problem we were working out earlier, the philanthropic problem. So to do this problem, we need to do the equation p hat plus or minus z score, p hat q hat over n square root, q hat being 1 minus p hat. So p hat is going to be x over n. And we need to know right here what is p hat. So that's this right here. So we're just calculating the sample proportion, which is going to be this right here. My plan is right. Oh, that's awesome. It's Kayla. That's so cool. Kayla. Well, we got a great history with Kayla's here. Kayla Beard and Kayla Gilm right there. No, thank you, Kayla. I'm honored to have you back as a student. I won't be putting up with you. You'll be doing excellently. And we were just doing some 320 earlier. Just got done teaching that class. I am honored that people want to take my classes more. No, that is awesome. You'll hear a lot of these same concepts. We were just talking about z-scores in, like, when you think of this, let me show you one thing real quick right here. This is the notes we are covering today for 320. I want you to tell me the following as I blink through it. What percent of observations would you expect? And I literally told them this. I literally drew it out again for them. What percent of observations would you expect to be between -2 and +2 right here? What percent of observations would you expect to be between -2 and +2? So what we were literally talking about the same concepts we talked about in 201 in 320. This is 320. And it's a different concept. It's leverage and deleted student times residuals. But I was like, well, what percent would we expect to be between a -2 and +2? It's just the empirical rule. It's just the empirical rule all over again. And between -2 and +2, we would expect 95%. Tiffany right there, 100 points, you got it. So these courses carry over. So anything outside of it's the normal model again. And these are going to be outliers. These are things that are unusual outside of these bands right here. There's another metric. We won't get into this topic right here. But it's just the normal model all over again. So that's actually what we're doing right here with this z-score. This z-score right here is where the middle 99% is going to be. So let's go ahead and grab our David M. Lane applet and look at where the middle 99% is. Now, I've done these a lot, so I automatically know this. Remember, we were talking about 95%, which is basically 2, basically. But this problem asks us for 99%. So remember, if you are doing any sort of confidence interval, The level of confidence it asks you for is going to be the z-score. Make sure to do value from an area and go between. Look how it shows you a plus or minus. This is the plus or minus for these numbers right here. So if it says 90%, there's the number. 95%, 98%, we're using 99%. So let's double check the work right here. We're just going to plug in the numbers. A lot of numbers to plug in, not with highlighter though. So with these numbers, we're going to plug in 0.0499 because that's p hat. Q hat is going to be 1 minus that. So Q hat is 0.9501, 1 minus P hat, 1 minus P hat. And then we go plus or minus because that's the margin of error. This is the z-score we just found. It's at the top of the screen, 2.5758. And then we square root, and this is where I go to write some big numbers, 0.0499 times 0.9501. There we go. So we're just plugging in the numbers, and then you have to carefully solve this. I always solve the top of this first. I'll do it slowly here, but watch how I solve it. This is, I think, the best way to solve it. I'm going to go P hat times Q hat right there, and then I hit enter. So that's P hat times Q hat, top part solved. Then I divide by 100,000. This is everything inside of the radical solved. So the next step is going to be to square root it, because you notice here we have the square root. So the next thing I'm going to do is square root it, if I could find it. There's the square root there. So this is everything right here. And so, yeah, yep, that sounds right. But then, and here's where you may have had an error. Now we have to times it by what, Tiffany? So now we have to do what to that value? Now we have to take this value that we just found for this whole thing, and we have to multiply that by 2.5758. And this is the what. We have just found the what by finding the whole thing right there. So we just found the what for this. So think about what we just found when we multiplied it by. And so what is this now? It's the plus or minus. So since this is the plus or minus, this is like me saying to you, I think dinner tonight will cost about $20 plus or minus $5. That's a what for the estimate. I square rooted it, and then I multiplied by 2.5. I think you didn't multiply by 2.5758 or 2.576. I think you forgot to multiply, Tiffany. I multiplied, you can see it right there, I multiplied it, I square rooted, multiplied. So I got to the same number you got to of the 0.006. Kind of variation, yeah, uncertainty, margin of error. So think about this. When we say like, just think of it this way, dinner's going to cost about $20 at the restaurant, plus or minus $5. Now you're not saying it's going to cost $15 to $25, but that's a measure of uncertainty. And that's what this margin of error is. The margin of error is just the plus or minus. So everything inside of here, which we just solved for that, is the plus or minus uncertainty on this. It's the, well, could be as high as this or could be as low as this. And it's the uncertainty. We have to add and subtract it. Add. So we're going to go right here and plus this. That was not plus it. We're going to go right here. I copied it. Oh, I got to solve it again because I deleted it. 0.04499 times 0.9501 divided by square root. So I'm square rooting it. Then multiply by 2.5758. That's the margin of error. I'm going to copy it. And then 0.0499 plus this. And that's the upper bound. Pause screen error on this. That's the upper bound. And 0.0499 minus this. That's the lower bound. I think you might not have multiplied it, Tiffany. Does that make sense? I think maybe it wasn't multiplied. So you have to multiply it by the z-score because this is the percent confidence. So I think you solved this right here, but then it wasn't multiplied by the z-score. I think that was the issue, I think. And yeah, good stuff right here. Good problem, good working out. There was another one. I think this is the mailer one we just did, right? So, and the mailer one is the same one. So we would just change the numbers on this if we were doing a different one. We'll do the multiple choice one here coming right up. Let's go check out the multiple choice. Let's go check out some multiple choice questions. Thank you so much for all these questions. A lot of good practice. We want to know as much theory as we can. So we want to get all of our theory down. I think the chapter quiz is working now. It was just like not saving when I would go to save it. Confidence intervals for proportions. preview of it. Confidence intervals for proportions. Place questions. Here we go. Let's take a look. Was it this one? Yep. Do you want to do a canvas content? We can do a canvas content for this. I think it was Tiffany. That sounds. Let me look at the number again that I got. That does sound accurate, Tiffany. 4.81. Yep. Great job, Tiffany. Hey, Calzone Tyrone. This is for you, Calzone Tyrone. For you, Calzone. I probably did that last time you showed up too. I think it rounds. Tell me if it's off by a tiny bit. Tell me if it's off by a tiny bit, Tiffany. Calzone is our fan favorite from New York. I gotta get my oldest from school. That's awesome right there. Enjoy. Calzone, fan favorite from New York, playing in our first Kahoots. Been here since the early days of Stat 201. The early days. Several factors influence confidence intervals among. Here we go. Let's check out a question right here. Several factors influencing confidence intervals. Here we go on Stat 201. You were here before we had maybe the transition stuff. I made that early on, maybe. So when we talk about confidence intervals right here, we're doing a formula. Hope you're doing all right, Calzone, up there in New York. Like, miss New York. New York's such a good place. Let's look at our confidence interval formula right here and try to solve it out. 100 points, Calzone, from our new MuBot. I don't know if you've seen MuBot even. So we got right here the formula. Okay. This is the key to solving all these questions. So with these questions right here, we are going to try to solve and think of the theory for each one of these. The theory is what's most important. So let's see. For a given sample size, some of these are tricky. Higher confidence means a smaller margin of error. What value on the screen right here controls the confidence? It's just saying everything else consistent. So what value right here controls the confidence? We've got p hat, we've got z, p hat, q hat, n. Is p hat the confidence? That's the sample proportion. Is z controlling the confidence? That's going to be the z-score relative to the percent confidence, maybe. I mean, that's what it is, but maybe that's the confidence. P hat is the sample proportion again. Q hat is the complement. So these both add up to 1, like if P hat is 0.2, Q hat's 0.8. And it's like when we go to a sample, if 20 out of 100 people, 100 being N, say that they like Taco Bell, I don't know why, it'd be 80 out of 100. And then this would be 20 out of 100 don't like it. Yeah, I did. That was a wink. Got some of my eye right there. So I think the z-score right here is going to control the confidence, right? So if we were to increase the z-score, like if we were to use the following z-score of like 1.96, or we were to write out a similar interval of p hat plus or minus p hat q hat over n square root, but the z-score were to be something like 2.5758, which is the z-score for a 99% confidence interval versus a z-score for a 95% confidence interval, then as we increase the confidence, the interval will get wetter. As we increase the confidence, the interval, because this is in the margin of error, the interval will get wetter. So what will happen is you make a more confident interval, Tiffany, and we can see it here visually, going from a 95 to a 99, the interval will get wetter. Ditto, good to see you here. We have a ditto in the chat. As we go from a 95 to a 99, the interval will get thisser. And we're showing it mathematically also here because it's a plus or minus, bigger, wider, because we're saying I'm more confident it'll be in the interval. So we're making a bigger interval. So that answers the first one. Let's look at it. The question says, for a given sample size, higher confidence means a smaller margin of error? Nope. False. It's just saying everything else the same. It's just saying higher confidence means smaller margin of error. They're just saying if sample size is the same. Because someone could be like, what if the sample size changes? For a specific confidence level, larger samples provide smaller margins of error. Okay, now it's asking about larger samples provide smaller margins of error. So let's go do 2 examples right here. And we're just going to take, and everything's going to be constant, but let's change one thing. So here we're just using some sort of z. And let's go out and talk to, let's say, let's go out and talk to 50 people. Or let's talk to 5,000 people. What do you notice about this? And it just theoretically, it makes sense, right, Tiffany? So theoretically, and look at it mathematically, this is in the denominator, right? So if you were to increase the sample size, your interval or your margin of error component, because this is all, I cannot click buttons today. This is all the margin of error. The margin of error is going to get smaller because you're going to be dividing by a bigger number right here. Does that make sense mathematically? And then theoretically, you're talking to more people, so your interval is going to get smaller because you're going to have more certainty. You're going to be less uncertain. You're going to be more confident. Oh, no. We don't want to say more confident because that sounds like we're talking about confidence levels. You're going to have a tighter interval, but you're not going to be, confidence is only controlled by the Z. Sorry, Brian almost misspoke. That's where confidence is controlled. The interval itself is going to be tighter, but the confidence level is going to remain consistent because the Z score has not changed. So going back to the problem right there, for a specific confidence level, larger samples provide smaller margins of error. That is true. Once again, showing you the mathematics right here. Mathematically, larger sample is going to make this quantity smaller, and this is the margin of error component after the plus or minus. So we see the margin, the mathematics, can't speak. For a fixed margin of error, larger samples provide greater confidence. Now, this one's weird. This is the question that has tricked me before. It won't today, though. It's saying for a fixed margin of error. So it's saying the margin of error here is equal to 0.04. And the margin of error here is equal to 0.04. So if we were to have this, and the margin of error is equal to the last component, the Z times P hat over Q n square, P hat times Q hat over n square root. So what it's saying is if we have two of these, it's best to always draw things out, see if it makes sense. Let me read it again. For a fixed margin of error, we have the same margin of error. Larger samples provide greater confidence. Okay. So if the sample size was larger right here, like this is 50 and this is 5,000, but we still need to equal up to 0.04, like this is still going to mathematically solve out. Well, what would happen right here? If theoretically this was something like 2.5, then what would need to counterbalance? So if the sample size was increasing, but everything else stayed the same, the Z-score would need to do what now? Correct, because it does. So the Z-score is the confidence. So it's saying, well, let's read it again. It says, for a fixed margin of error, larger samples provide greater confidence. So the sample size is not doing the confidence. This is the n down here, which is the sample size. And it's saying that this is fixed. This is not changing. That's what it means by fixed right there, for a fixed margin of error. So if we keep this constant, but sample size goes up, what would need to happen to the Z-score? So the Z-score would need to do what right here to counterbalance the sample size? Because this is going to solve out to 0.04 either way. So the sample size isn't the confidence, but to have a fixed margin of error, this is like the weirdest theory question ever. But to have a fixed margin of error, the Z-score is going to have to do what right now? Because it's going to try to counterbalance that 50. As 50 goes up, the Z-score is going to do what? Because this is going to mathematically solve out to 0.04 both times. So if this is 2.5 here and this is 50, if this increases, this is going to have to do what? The Z-score is going to have to do what? The Z-score, to counterbalance it because n is going up, the Z-score is going to have to do what? I'm pretty sure it's going to have to go down. Let me think right here. No, it's actually going to go up, right? Yeah, no, that's actually, you are correct. Sorry, I misspoke. Because that's getting smaller. So the Z-score is going to have to get bigger because it's in the denominator. Tiffany, 100 points right there. Brian almost got something wrong. No, it'll actually go up. No, that's all right. I actually misspoke. This is a tough theory one. Just do something here. Let's make it a lot easier. Here's a way to, I'm going to make it a lot easier with the mathematics. I'll show you. That's like, looks really complicated, right? Let's make it look a lot easier. If I tell you that this is 4 and this is equal to 2 and this is equal to, no, it can't be 4. Here, we'll do this. Yeah, because this will be equal to 4. Yeah, there we go. That's right. Okay. And now we go down here to the bottom. These are the numbers we're going to change. So now, because this is similar in mathematics, the way it works. And now this is still equal to 4 down here. But what changes is this becomes 10. So now what is the z-score going to have to do? This is the same components. This is the same components as margin of error equals to z p hat q hat over n. And I hope this helps make more sense of it. It's the same components, but what would this, for this to be the same thing, because we're increasing the n right here, what would the z have to be? And so I'm solving it in my head right now. Okay, I think I got it. Yeah, it makes sense. What would it have to be? The z is going to have to do what? The z-score, which controls the confidence. And you could just say what it... Hopefully that makes sense. This is a little bit easier numbers to work with, and we can actually solve this mathematically. It's still just the same components where this is the margin of error. It's just the same components right here, but with numbers that are much easier to work with. So it's the exact same components. And we're just asking, it's not literally the same formula. It's going to have to go up. Does that make more sense, Tiffany, right here? If we plug it in theoretically this way, we're saying if the sample size increases right here, with this being fixed right here, like this is fixed, like this is not changing. It's saying the margin of error is fixed, which is the value over here. The margin of error is fixed. Thus, if the sample size goes up, which is n, which is in this position here, then the z-score is also going to have to go up, and this would actually become 20. So the z-score, which controls confidence, yeah, hopefully, sometimes it's like I just want to visualize it in a way that's like, oh, that makes sense. So that is what's going on there with the formula, and easier numbers make things easier. So is it true that for a fixed margin of error, larger samples provide more confidence? That is true. For a given confidence level, having the margin of error requires a sample size. Okay, yeah, this is easy. This one is actually in another question. So if we want to take, this is from a previous homework question too. This one's going to be false. If we have a margin of error right here, which is going to be this, no, not that, z-score. And we want to get 1/2 of it. Well, what would we have to do? Do you remember this trick from a previous homework assignment? To get half the margin of error, we would actually need what the sample size. And this is from a previous assignment. You can't just join these into the radical. The way to get it into the radical is to square this, but you don't want to square it. You want to undo it and square root it. So the answer is, to get half the margin of error requires what the sample size? Well, when you combine it under the radical, you'll see right there, that means you get to pick it based on the percent confidence. If you reduce and combine under the radical, you need 4 times the sample size. This is from a previous assignment too. And so you can't just times things by 1/2 under the radical to say how much more sample size do we need. 1 squared over 2 squared square rooted is 1/2. So this is 1/2. We're just squaring it and square rooting it. The whole point of doing this is so that we can combine it. You could just write it as, like, if that's too complex, you could just write it as square root 1/4. And remember, 1/4 square root, if you were to go here and take 1/4, what? If you were to take 1/4 and square root it, you get 1 divided by 4 square root, and you get 1/2. So the square root of 1/4 is 1/2. So this is 1/2. We're saying we want to times this by 1/2, but we're calling it square root of 1/4 so we can combine them. Does that make sense, Tiffany, right there? So the answer to this one is definitely false, because it wouldn't require twice the sample size. It would require 4 times the sample size. There we go. Little tricky, a lot of theory right there on these. Understanding the equations is good, and just practicing knowing what it means. Let's do more questions. Let's do more questions. Here we go. Know your formulas. Know how to use those formulas. What questions do we have? Let's see if emails are doing all right. We had problems with the quiz. I think that's fixed up. No one has said it's not working yet. We had some not workings. Let's see here. Endless Toys R Us sale. What? Let's see if anything major jumps out to me. Oh man, they did the... Man, the bowl fountain had orange in it. Looks so cool. What question? Can you check the problem? A philanthropic organization sent emails, random sample. What is the percent confidence on that? What is the percent confidence? I think you didn't multiply by the z. So what is the percent confidence? I think maybe you didn't multiply by the z. Is it 95, 98, 99, 90? I'll find the 90%, so 1.645 is the z-score. It might be that. That seems a little... And square root. Is that right? Let me think. I think you didn't multiply by the z-score, Tiffany. Double check your work. That doesn't look accurate. Double check. I think maybe the z-score wasn't multiplied by. Tell me, when you get your margin of error, tell me your margin of error. So find the margin of error and tell me your margin of error. So double check your margin of error and see if you get your margin of error. We'll do another problem here. So double check your work for margin of error. We'll do another problem here, but double check your work for margin of error. So big thing for the test, so make sure you can get it. Tell me when you get your margin of error, and I will confirm the margin of error when you solve for that. So more questions. See if I will confirm the margin of error if you tell me the margin of error. I think the z-score wasn't multiplied by. I think I'm trying to see mathematically here. I think that seems right. Let me divide by it. Yeah, it looks like the z-score wasn't. You didn't multiply by the z-score, Tiffany. So, yep, Tiffany, 100 points. So, and do you see it, Tiffany? Now your interval is going to be wider. So great job, Tiffany. So yeah, and then you can confirm the answer to me next right there, which I can kind of see it. I'll write it back in here in the background. Great job, Tiffany. Excellent work. I think you just didn't... Here I've got... 6. What? What am I doing? Oh, I don't have it stored. I've got the upper bound. Just make sure it's symmetric. I know the upper bound of your interval right now. So I think the first time it wasn't multiplied by. If you want to tell me the upper bound, lower bound, I can confirm. Great work, Tiffany. Great practice. You're getting it down. And just double check. It's good practice. Good practice. Get those assignments done. Almost back on my sleep schedule. Almost back normal. Got everything working there. TA question. Awesome. TA's holding office hours. Looking to see what's going on. Sports. General chat. What are people saying in general chat? Someone's got a TikTok? I'm scared. Wait, I'm playing something copyright on stream. I don't know if that's copyright. If you have questions, let me know. What questions are there? Such a relaxing day. If you have questions, put them in the chat. Let's see right here. Trying to see if we see any other major stuff. What is... I have no idea what this is. Seeing what I have via emails real quick right here. If you have a question, put it in the chat. We're just chilling out right now on Stat 201 if you swing by. Go. Let's see. Any questions? Let me see. Yep. That's got it. Great job, Tiffany. Excellent work. Replying to a few quick emails here in the background. Where's that one? I got it. Do a poll. What is the next problem? Whoever has the next problem, we will start it up. You're welcome, Tiffany. Great job. If you have more questions, Tiffany, let me know. I'm going through and replying to some emails, making sure I'm decently caught up. Sometimes it can be pretty quick. We have meetings tonight. And so tonight I have meetings, so I want to make sure. Awesome. Student pilot graduate. Library carrot. Go see what questions are. It's just chill time. If you have a question, let me know. It is chill time right now. Who's here? Who's asking? Who's got a question? I'm just literally going through, getting caught up on everything. I don't see any questions. No. I think it's because got my grocery order in for later today. Let's see. Oh my gosh. Dr. Lou is amazing. I have no idea. I just got an email from you. Let's see. Nice job, Tiffany. Great job. 100 there, Tiffany. I'm just here chilling out. Getting caught up on everything. Kind of caught up. I don't know. I don't want to end office hours early. Are there any questions? Who's here with questions? I'm going to see over here. See what someone said. Hey, Brian, on number 7, I noticed the two associate functions do the same Spearman correlation, but given if you how possible, correct? Number 7. So, trying to read there. Make sure to. I think I see. Yeah. You want to do some chapter 14 quiz? Let's do that. I'm just chilling out right now, knocking out some emails and Discord messages. So, and thank you to everyone. This is why I'm here, is to like answer questions. So I was like, well, I'm gonna knock out some Discord messages and stuff like that. I'm like, okay, let me go right here. Let's go check that out. Chill time right here. Which one do I want to play? Let's go check this out. Chapter 14. So you're talking about the confidence interval for the means, Tiffany? Ooh. How far did the Golfers Country Club? Yeah. Chapter 14. Tiffany, you're so good at working ahead. This is awesome. Let's go check it out. Let's go to the Golfers at the Country Club. And thank you, Tiffany. Like, it was a week ago. No, it was Tuesday the following week where I was really out of it. Man, I was not doing good. Enough of that. Enough of that. Let's go look at the Golfers at the Country Club. We'll go out to the Country Club right now. Where are you, Golfers at a Country Club? I'm looking for the question. Really? Hey, found it. Let's go check it out. Yeah, no, that's the way to do it. Tiffany, 100 points right there. Get things done early, have them done, and then practice and review and get ready for tests. So that way you can just like refresh your memory. The more you practice it, the better you do it. Let's go check out this question here. Golfers at a Country Club. Here we go. So this question right here, for what kind of data? 3-letter word. Think about what this means right here. This is the true driving distance, which is what we're trying to estimate from a sample of driving distances, and we're trying to estimate the true mean. So we've been doing a lot of confidence intervals today, and we've been using this equation right here. But so this is a different chapter. This is chapter 14, confidence interval for the mean, because that first interval was a confidence interval for the what? The first interval we did right here is not a confidence interval for the mean. This is a good way to compare and contrast. This is a confidence interval for the mean. That first interval is a confidence interval for the what? That first interval is not a confidence interval for the mean. What does that P stand for? Well, we're making it from the sample proportion. So it's a confidence interval for the true proportion. The confidence interval down here is made from the sample mean and is now a confidence interval to estimate the true mean. So we're going to use this formula right here because we have the sample mean plus or minus the t-statistic with n-1 degrees of freedom. More on that in a moment. With the sample standard deviation divided by the square root of n. So we'll learn this formula right here and how to use it to solve this problem. So for this problem right here, we are given information. This information is very important because it's going to be the notation we need to solve this problem. We also probably need that 202. 202 is the what for this problem. Let's grab the problem right here, drop it in, and see if we can solve it. So for this problem, we need the notation. The notation we need, yeah, let's do that one next. You got it, Catherine, you bet. Thank you so much, Catherine. We'll do that one next, you got it. So we have here, the sample mean is y bar. The standard deviation from a sample is this. I'm going to kind of go this a little bit quicker. And so there we go. Now the hard part about these problems, which we haven't talked about yet, is in this formula, the t-statistic, which is our confidence, is based on what is called degrees of freedom. The degrees of freedom is n-1, so we'll solve that here in a second. It's degrees of freedom, 201. This is for a one sample t. The degrees of freedom are n-1. So now we plug in 8.6 over, let's not plug those in yet. Let's write the equation. S and then n square root, s over square root of n. And so now we're going to plug in our numbers right here, which we have. We'll plug in the t-statistic in a moment. So the y bar is 285.6 plus or minus, that t will come here shortly, 8.6 over square root of 202. Now the t-statistic is the more complicated thing to talk about. T-statistic was created by William Gossett, who Ronald Fisher did not like him. There was a statistician battle. A lot of those have happened in the day. And he made a better way of doing the z-statistic. So what you're about to see right here is basically the z-statistic, but it's more accurate. So here is the normal curve. Looks like a bell-shaped normal curve right there. Here's the t-curve. The t-curve has with it degrees of freedom. Very quickly, the t, when it has fewer degrees of freedom, is more smashed down. Mr. T says, I pay the fool, and smashes it down. But then he gives it freedom to be normal. Our t-curve has 201 degrees of freedom, which then we can go in and find out. I think we're doing a 95% confidence. We're doing 95% confidence, and that would mean 5% is on the outside, or if you prefer classically, 95% on the inside. This is the t-statistic, and that's very close to the normal curve's 1.96. We lost it right there, but do remember we just typed in the degrees of freedom, and then we put in the percent confidence, and I like to shade the middle because that's what we're talking about. The middle 95% is shaded. So the t-statistic is based on degrees of freedom, and it's kind of like the normal. Numbers will be closer to the normal the larger the sample size, which increases the degrees of freedom. We'll go over this more in depth, but this is a more of an advanced lecture right now, but that's the equation. This is where these numbers are coming from. The harder part right here is going to the t-applet and getting the t-statistic. You need to go to the applet I put in the chat right there, and probably everyone's going to have the same one. Why did we put in 201? So Tiffany, great question. So take a moment right here, Tiffany, and look right here and look at how the degrees of freedom are calculated. I could go into the theory why it's n-1, but the sample size here was 202, which makes the degrees of freedom, that's the notation right there for the degrees of freedom. This is a t with n-1 degrees of freedom. You don't multiply it by that. This says a t that we will pick. Yeah, no, Tiffany, 100 points. Thank you for asking these questions. For a one sample t, the degrees of freedom are n-1. It'll get more complex as we do other questions. Not super complex, but we'll talk about those when we get to those chapters. The two sample t. It's not n-2. But from here, we just solve the equation. The first thing I'm going to do, so watch the steps carefully here, is I'm going to take 202 and I'm going to square root it. So that's the square root of 202. I'm going to copy that. This is the square root of 202. So then I'm going to go 8.6 divided by that number I just found. That is this whole portion of the equation now. And now I'm going to multiply that by 1.972. And I've just found the what for this question. So just like every other interval we've been solving today, this is now the what for this question. It's in the plus or minus. Oh, you got it. Yeah. So this is the margin of error, the plus or minus on it. That is the margin of error. Remember the steps again. I'll repeat the steps right here again. Take 202, square root it. That's the square root of 202. Copy it or write it down, whatever you prefer. Take 8.6 and divide by that number. Now you've solved this right here. So then multiply that by 1.972, and you now have the margin of error. So now we're just going to do plus or minus on the 285.6. 285.6 plus this. And so that is this value, 286. And then 285.6 minus this, 284.4. And it says one decimal. Let me double check. 285.6. There we go. 286.8. Yep. So that's got it right there. Just double check the mathematics. What is the problem with this experiment right here? So this experiment's a little bit of a weird one. They went to golfers at a country club. I think they went to the best golfers and they took the averages of golfers. Oh yeah, they took the top golfers, so it's not random. Condition 1, random. Condition 2, less than 10%. Condition 3, nearly normal for this one. More on that when we get to it. The data are the mean driving distances for each golfer. Is that a concern for the interval? So how I got 200s? The 202 is the number of golfers. The 202 is the sample size, the number of golfers. And so that's the count right here, the observations. That's the sample size right there. And then this is the sample mean right here. That's the Y bar. And that's the S right here. And yeah, I think I should do it. Which one are you thinking about, Tiffany? Which one are you thinking about here on the work on this right here? The 2856 is the Y bar, and the T statistic is found via the calculator. But yeah, which screen do you want me to go back to? Do you want me to stay here? Because you might have typed that when I was switching screens. Do you want me to stay on this screen? The sample size is 202, and that'll go down here in sample size. The standard deviation of the sample is 8.6, and that's sample size right there too. The mean of the sample is 285.6. That's the mean right there of the sample. That might be the right margin of error. Is that what I got for mine? Still got it in my copy paste, right? Yeah, that sounds accurate. Great job, Tiffany. And then that's your margin of error. So that is your margin of error. Now you want to add and subtract that to the mean. Because that's the margin of error. That's like the plus or minus. You're like, well, this is my plus or minus on this. Tiffany, great job. You're getting it down. And this is just how we make confidence intervals. We figure out the margin of error for the interval, and then we go plus or minus a certain amount. So yours looks similar to mine. Like when you solve this full equation right here, you get something about like this. This is the solve of the equation. So we're just showing it that 285.6 plus or minus this. Great job, Tiffany. You're getting it down. And then once again, I'll show the other parts of it again. Only the top golfers were chosen, so it wasn't random. And then also, it's going to be biased because it's the top golfers. So there's going to be some bias, and they're using the mean. So I've never seen us ask a conceptual question on that on the test, but the mean, this is the mean of the mean. So it's a confidence interval for the mean of the mean for top golfers. It's a weird thing. This is not the best statistics in the world. This one, that they're trying to point that out to you. So that's got it. That is the question. So we will hop here to the next question. We got this. Catherine asked the question about the CO2 emissions. Let's go check out those CO2 emissions on cars. Let's go check it out. CO2 emissions on cars. CO2 car emissions. Oh, I can't wait for the weekend. Chapter 13, CO2 car emissions. Sampling distribution of sample proportion. Chapter 13, homework. Let's do the homework version of it. And here we go. Yeah, it sounds about right. But reverse them, reverse them. You might have your lower and your upper reversed. Lower number on the lower side, upper number on the upper side. Lower number on the lower side, upper number on the upper side. Make sure it's 285.6. Let me see again. Yeah. Make sure it's reversed. Lower number on lower side, upper number on upper side. Because it's like from this low number to this high number. I was like, oh no. But it's not on the. It's on the quiz, I think. Oh no, this is chapter. I went to the wrong one. That's why it's not there. I went to the wrong one. I was like, where is it? Sample distribution for sample mean homework. Here we go, Catherine. 2 seconds. We'll have it pulled up. Doing the CO2 emissions. Let's go check it out here. What are the changes? Like, yeah, I'll do one next. You got it. Let's do the flight question next on the intervals, which these are both on means. So this is another means one. You'll notice some similarities in the formulas here. See if you catch them. Let's check out this question on CO2 emissions. So for this question right here, we're trying to figure out what we might see in a fleet of cars. This is going from a population to a sample. Apparently, we know the truth. So we know the truth for this sample, right? Or the population, excuse me. We know the truth for the population of the cars is that the mean of the emissions of these cars is equal to that 3.439. So this is the mean emissions. It's the truth. Remember the steps we do? We always mark our notation to start. So we know the truth for the cars is this. That makes it mu. This is not from a sample. You might be saying, well, will they see a sample size? This is saying what might we see in a sample if we took a sample. This question is the sampling distribution questions where we're saying we know the truth. And if we meet the conditions of randomly selected data, less than 10% of the population being selected, and large enough n, because it's quantitative, pause there, then we will say that it is normally distributed, that's if we meet the conditions, with a mean of mu and a standard deviation of, wait for it, sigma over square root of n. So go ahead and take a moment right here and see if you can solve what this distribution will look like. Well, the first number is easy. What's the first number going to be? Well, we already know what mu is. Mu is just going to be 3.439 because the mean does not change for the distribution of the sample mean. This is the formula right here that the mean for the distribution of the sample mean is equal to the true mean. Well, the standard deviation, which we have for the second part of the sample mean, is equal to sigma over square root of n, which you see right there. So all we need to do is take our sigma, which our sigma is 0.06, and divide it by the square root of 80. So now we're going to take this and just mathematically solve it to get the new standard deviation. And this is where the curve gets tighter, if you remember how the central limit theorem works. 80 square root, where's my square root? 80 square root 0.6 divided by it, 0.0671. There we go. New standard deviation, which is tighter. And now what will we do? We're going to call upon our friend right here. Now on the test, David, on the test, you wouldn't have the David M. Lane applet, but some of these can be solved without it. We could actually get guesstimates by drawing the curve ourselves. We'll go to David M. Lane here in a second, but what I'm going to do is I'm going to draw the curve and use rounded numbers. Using rounded numbers, I'm just going to round to 2 decimal places right here. 3.44, that's rounded of that number. And then the other one I'm going to use 7%. So I'm going to use guesstimates as though I don't have David M. Lane, just to show you. I'm going up 1 standard deviation, and I'm using this as 0.07 right here. So that's one of those standard deviations going up. I should change colors to make it clear. But I'm going up 1 standard deviation, which I'm rounding to 0.07. And then we're just going up another standard deviation. This is a rounded version. This will not get us the exact answer. It's just showing how we could solve it on a test without the applet. So we would probably carry more decimals on the test, but this is just to help with seeing it all and to show what we could do without the David M. Lane. So the first question asks us, how will the curve look? Well, the curve is going to be normally distributed with a mean of the mean. This is what we just solved for. And a standard deviation of this right here rounded to 3 decimal places right there. That's what we solved for. Now it asks, what is the probability of between 3.5 to 6? 3.5 to 6 would be somewhere in the region of here to about here. And if you look at that, that's almost inside of, if you remember your empirical rule numbers, this is 34, 13.5, and that's a little bigger than 13.5. Because this is, if you break down the curve, it's a totally different thing to do, but we know the numbers from the 68, 95, 99.7. That's the 13.5 right there. If you remember how that one works, I'll move it over here so you can see it a little bit better. But that's the 13.5 when you break down the curve. And so if I use that number to make a guess, I would probably say it's a little bit more than that. And so let me just think here. Computing it in my head very quickly. So I'm going to say that. Oh no. We're not going to guess it today. That's my last guess. You do only get 2 guesses on it, and then the last one you get it wrong if you get it wrong. So there's the standard deviation, and we got to put in the mean, 3.439. And then we're going between 3.5 to 3.6, right? I hate how it sometimes doesn't plot the last number. It's a little bit further over, so it was 17%. My drawing is decent. There's my drawing. And there's the actual. What do you think? Decent drawing? Did I do an all? I don't know. I should have carried more decimals, right? It went a little bit over, so I underestimated it. I thought it was closer to like, what did I put? 14% or something? My last guess was it's 17.3. And my last guess was this. So I was off by about 2%. And so, you know, we got a decent guess in there, decent guess, but the last one, the top 10%, this one we can get. Knowing how our curve works, we can actually guess this one. The top 10%, it's actually going to be a little bit tough today. This is where the top 16% is, because of the 68, 32. And this is where the top 2.5% is. So the top 10%, oh, it's such a tough one. It's going to be right in here. No, it's 1.28. I know the z-score for it. It's going to be over here then. So I'm going to say that rounds down to 3.5. That rounds down because it only wants to 1 decimal. So I'm going to say that rounds down to 3.5 where the top 10% is. Oh, I put 2.5. That's an error. That's an error. There we go. So that one we were able to figure out, but once again, we can use the David M. Lane applet by going here and taking our mean and our standard deviation and putting in the standard deviation, putting in the mean, and asking for where the top 10% is. So right now, if you notice, and notice my drawing too, if you look at my drawing right here, I was able to identify about where that would be at. If I shade this in, then we could have made a guesstimate. And if you notice, my numbers kind of rounded their numbers. But this is what you want to try to practice to do because I can kind of get ideas for where things are at. So I said, oh, that's probably going to round down, and it does to 3.5. We could give you, like we could put in like 3.4 different numbers. The top 10% has to be above the mean, and it also has to be above the 16th percentile and below the 2.5th. So if you were to draw this curve, you would know these numbers it has to be between. So if we gave you something like 3.46 or 3.65, then like as a multiple choice question, these numbers have to be wrong. It has to be between these numbers. So a lot of times people say, well, how could you ask this on a test? A multiple choice question of like which one of these is the top 10%, because a drawing right here narrows down the possibilities and we can see the answer. And once again, the David M. Lane is just carrying more decimals. If you delete some of these, sometimes it shows those extra things, but that's not enough decimal place accuracy. But this is a great question right here to practice and know how to draw the sampling distribution of the sample mean. And now we're going to do a similar type thing and do confidence intervals for the mean. So let's check this out with confidence intervals for the mean. So this is a new chapter right here, which we haven't done, which will be on test 3. And it's really good material. This is going to be confidence intervals for the mean. So hopefully that helped out right there, Catherine. Great question, Catherine. Thank you so much. Confidence intervals for the mean. Let's go check out the confidence intervals for the mean right here. And this one, the question is, what are the chances your flight leave on time? Wait. I saw something different. There's a flight one here, but I think it's a different one. No, I think this is the right one. Tiffany, correct me if I'm wrong. Let's go check it out. Here we go. Let's check out what is the chances your flight will leave on time. You're welcome, Catherine. Excellent work. Thank you so much, Catherine. Here we go. What are the chances your flight will leave on time? We're going to make a confidence interval to check this right here. And so we are going to look at flights each month from 2001 to 2006. And we have a histogram over here representing it. 72 observations, sample mean, which is where the mean of the distribution is at, and a standard deviation of 2.6. So they're looking at the mean amount of flight leaving on time and a probability of this. Let's go check it out. And hop in here, jump in, and do it. So to solve this question right here, we need to take the following. We need to take and use an equation, which means we need to know our notation. This question is so nice, though. It basically gave us the notation. So instead of them asking you to write out the notation, you get all the notation for free right here. But you're missing one thing. Tiffany, do you remember what we can solve for using n? So I'll give you a hint. I'll start writing out the formula we're going to use. We're going to solve for a confidence interval for the mean. So that means we need the sample mean plus or minus the t-statistic and a little thing down here. And then we're going to go right here and do s over square root of n, which is similar to that sigma we were just using, but we don't know the truth anymore. So we actually need to solve for the degrees of freedom. And this formula is pretty plug and play. If we go right here and put in the mean of 24.5139 plus or minus, we'll skip the t for a moment because we don't have that yet, 2.60320 over 72. Now, you do not multiply these numbers. That's not a multiply. This is based on the confidence, hence the star. We'll pick a t-statistic. This is going to be a 99% confidence interval, and we need to go over to Mr. T-Zaplet, and we're going to use the T-Applet to find the t-statistic. But every t-distribution has with it this. What does every t-distribution have? Whenever we talk about a t-distribution, it'll always have this with it. Every t-distribution will always have this. Whenever we talk about a t-distribution, we always need to mention the what's for it. Key thing you should know. If I say we're using the t, you should say, well, what are the this for it? Because I have to know the this for it to be able to calculate the t-statistic. Brian, you must tell me those this for this t-distribution. You must tell me the what's for this. You must tell me the what's for your t. How many this it has. And it's right over here. You must tell me your degrees of freedom. The less degrees of freedom it has, the more it's smashed down. Mr. T comes in, smashes it down. The more degrees of freedom it has, the less it's smashed down, and the more it looks like that normal curve, and we see that 1.96. This is a more exact calculation than the T curve, the Z curve. Here's the Z curve, here's the T curve. This calculates based on the sample size, and we do the sample size minus 1. So the degrees of freedom for my problem will be n minus 1. All we do is take the sample size minus 1 to get the degrees of freedom for a one sample t. So it's 72 minus 1. Now I need to give 99% confidence, and I like to shade the middle area. So we could shade the middle 90, or, as the problem states, we should shade the middle 99%. This means the t-statistic is 2.647. So now we know our t-statistic to create this interval. 2.647. And from here, I forgot my square root. From here, it's just solving the equations. So we take 72, square root it, and we copy that. Then we take 2.60320, divide by this, and there we go. That should be accurate. Multiply by 2.647, and now we have the margin of error. This is the margin of error. Just write down your work as you go, solve the equation, and get the margin of error. So it's 24.5139 plus or minus this. That is going to be the margin of error. Just solve your work. We'll solve one more time here. 72, we're going to square root that. We're going to copy that and do 2.603022320 divided by that. So now we've solved out this portion right here. We're going to multiply that by 2.647, and that's the margin of error. That is now the margin of error, and we can just do plus or minus this. So let's solve it. 24, I'm going to copy this before I forget. 24.5139 plus this, 25.33. And then 24.5139 minus this, 23.07. Or 70 right there. Should be right? Two decimals, two decimals. Which one are you wondering about, Tiffany? Which one are you wondering about? Just ask me, like, how did you get this? How did you get that? Which one are you wondering about? Which value are you wondering about right here for the equations? Just make sure you have your equation written down. Which values are you wondering about in this equation? Let me know. And which? Yep. Which values are you wondering about? Like the T, the S, the N? Nope, won't be on the exam next week. We're just working ahead. Casey, if you have a question, let me know. Great stuff right here. We got time for at least one more, I think. So which one, what were you wondering about for this right here? Anything you want to know about? We can work another question after this. That's found by the what? How do we find that, Tiffany? We need to go where? Where do we need to go to get the t-statistic? Where should we go to get the t-statistic? The t-statistic is how confident we are. It controls the confidence. So the t-statistic will be obtained via t-applet. So what must I know for every t? I must know this. Yep. Great job. So then every t has with it a this. Every single t always has a this. Every single t, we must always know this. Whenever we're talking about the t, you must tell me the what's for this. Oh, Casey, that's awesome. Thank you, Casey, right there. I need to add those to the exam page. Send out reminders about the exam. We don't have them on the exam page right now. What? Speedruns are great practice. I need to update like the exam 2 playlist. 9. Every single T has with it what? Whenever you talk to me about the T, you must tell me this for the T. Whenever you're talking about the T, you must tell me this for the T. You're talking to me about a T statistic? Well, what are its whats? Anytime you do a T statistic, I must know the this for this. Every single T will have with it what's. Not quite you can use it to find p-values with degrees of freedom. Degrees of freedom are basically how normal it looks. Like I could go into more detail about it. But the degrees of freedom control the shape of the T distribution. So the more degrees of freedom it has, the more normal it looks. Look at as I delete these, it becomes less normal. It gets more smashed down. And so how would we know the degrees of freedom for this? How would we know the degrees of freedom? The degrees of freedom control the shape of the T distribution. And so here's the notation for it. How would we know the degrees of freedom for the T? So how could you calculate? It wouldn't be 72. It would be what? So you're close, Tiffany. You got it. It's not going to be 72 degrees of freedom. It would be what degrees of freedom? For the one sample T, this is the formula for it right here. This is the degrees of freedom. So this is not a multiply thing. It's saying a T with n minus 1 degrees of freedom. 71. Great job, Tiffany. You got it. So we're just going to type 71 in right here. And then a confidence interval will always shade the what portion of the data, the middle portion, And then we're going to go right here and type 99. And now I've shaded the middle 99% of the curve. So this is a T with 71 degrees of freedom where I've shaded the middle 99% of the curve. Does that make sense, Tiffany? This is a T with 71 degrees of freedom, because remember the sample size here was 72, so 71 degrees of freedom. And then the problem asked me for 99% confidence, so I'm going to shade the middle 99%. And this is like we were doing with normal curves where we shade the middle area based on, it does say p-value right here, it does say that, but this is just how confident we are. Great job, Tiffany. What you're doing right now is something we haven't covered, so you're getting ahead, and then just keep reinforcing the knowledge. When you get to test, you'll be like, oh, cool, that's how confident we are based on the T. The degrees of freedom are based on the sample size. One sample T is n-1. That controls the shape of the T distribution. If it is a different sample size, it'll change the T statistic. So you notice how the T statistic here is changing because the T is based on a sample size, which controls the degrees of freedom. It won't always be 99%. It could be something like 90. But do you remember how when I was doing the normal curve, I would solve problems and I'd be like, oh, you want a 99% confidence interval? Well, 99% confidence interval is 2.576. And so, oh, wait, that's the z-score. I would say 2.576. Or I'd say 95, 1.96. The t-curve doesn't work this way. The t-curve, the values on the t-curve will change based on the degrees of freedom. They will approach the normal curve numbers, but the t-curve numbers are different based on the degrees of freedom. Jacob, good to see you here. So does that make sense that the t and the z are basically the same, but the normal curve will always have the same answers? Like I know this is 1.645. I know this is 1.282. So I know these numbers, but on the t-curve, the numbers change based on the degrees of freedom. It's like the normal, but it's basically a more exact way, and it's used for the mean. So whenever we're doing stuff with the mean, we will use the t-curve. So remember like mu t or Mr. T is mean. I'm sure he's a nice guy. I just like to say Mr. T is mean because the t-curve is used for means. So whenever we're doing stuff with means here for confidence intervals, we will use the t-curve. So the t-curve is used for means because mu t, like ut. So mu is the mean. So the number we need. Yep. The number we need is right here, the 2.647. And so now we have here the standard deviation and the sample size and the y bar. So you look where we take the y bar. This is the t we found, 2.647. This is the standard deviation of S, which is just sample standard deviation. And this is the sample size, how many people we spoke to. So this is like the percent of flights delayed, and we're doing it as a quantitative amount. It's not like one flight being delayed. It's like this month, 24% were delayed. So that's a quantitative amount because it's real numbers. And then the standard deviation, which is the variation among these months. We see a sample variation among the 72 months collected of 2.6. That sounds accurate. That's your margin of error. So that sounds accurate. Let me think here. 8.6, that should be, or no, 0.86. Did I get about 20? Yeah, that's right. That sounds accurate. There's mine right there. Mine's 0.81. Is your y bar, the y bar is this? The y bar is 80.75. It might be. We must double check. It's as long as this is 80.75, then add and subtract. Did they really change that question this much? Let me look at some other versions of it. I think all the assumptions are met. Interpret the interval. We can be 99% confident that the interval contains the true mean month, the percentage of daily flights delayed. There we go. And so I am blank percent confident that the true blank is contained in the interval blank to blank. And all the assumptions are met, which are it divides up the independence assumption right here from the randomization, but I always just do random means independent. And then the nearly normal is the way we're doing basically large enough n right now. So random, 10%, and then nearly normal, which is basically large enough n, which we talked about last class. But this is a chapter we haven't covered yet. And does it ever jump it to 80-ish%? There might be a slightly different version of this. Mine's always doing in the 20s. Double check that number up there is like 80% or something. If it says y bar is 80%, there might be another version of this that jumps it to the 80%. Yeah, there is. 90%. So if you want a 90% confidence interval, so Tiffany, I want you to help me out here. So I want you to tell me what the t-score for a 90% confidence interval is with 71 degrees of freedom. What is the t-score for a 90% confidence interval with 71 degrees of freedom? So I want you to find it, and I want you to tell me, and I'll confirm it. I've got a guess in my head right now. I know what it's pretty close to. I could guess it. I have a guess. I'm guessing. Last one. That's my guess. I'm guessing it though. I think I've like worked this one. Maybe watch it be exactly that, because I swear I've worked it, but it'll be something like that. I won't be too far off. But what do you get? T-score. That looks accurate. I'll double check your work. I think you're right. So we need to go to 71 degrees of freedom because sample size 72. We need to go between. Best way to look at it. And you're right. You got it. Sorry about that. Yeah, sorry. There's two versions apparently. But the T-score, you are correct though. I'm sorry, Diviny. It's the same problem though. And I think all the conditions are met. I didn't know the problem is virtually identical. I'm sorry, Diviny. Good practice. Hey! But the formula is going to be the same. It's just that the T statistic is changing because the confidence changed. So the only thing that changes right here is the T. Does that make sense? Always check the confidence though. Sorry about that, Tiffany. Mine was 99. Yours was 90. So this, just make sure it's the 90% confident T-score, which we see right here. There's the T for the 90% confidence. Mine was 99. And notice that's a bigger T. You got this, Tiffany. We'll see what last questions there are. Remember, quick snack before last class of the day, of the week. Last class of the week. Flyers. I'm excited getting some new groceries tonight. That's the high point of my week, getting groceries. Sounds sad. Well, with that, we'll see if there's any last questions here. Hopping back to the main screen. Yes, that does sound accurate because you have a much smaller T statistic. So if you look at the last one we got was like 0.865. So this one, instead of using a larger T, we're using a smaller T. That sounds accurate for the margin of error. That sounds like the correct margin of error. And so what you could have done, watch this, Tiffany. You ready for this? I'll show you a trick. Wrong button. So if you remember, you had this number right here previously. So I'm going to divide that by 2.6. What was it? What was that number? So I'm going to take this and divide it by 2.647. And that's what we call the standard error. And then I'm going to multiply that by 1.667. And there you go. Down to the decimal. So basically I brought it back. We shouldn't multiply it by that number. This is my problem right here. So I divided it by that to undo it. Because if you multiply something, you can undo by dividing. And then I multiplied it by the correct number, 1.667. So just kind of undoing the work. It's like, well, wait, we shouldn't multiply by that. Divide that back out. And then multiply. And then just add and subtract. And you got it. You got it, Tiffany. You got this. So now just take the margin of error right here like you've been doing. This is the margin of error. Do remember, everything after the plus or minus is the margin of error component. Everything in this formula right here is the margin of error component. The things we should know theoretically wise. The margin of error component is everything after the plus or minus. We repeat that to ourselves. The margin of error is everything after the plus or minus. It's like this plus or minus this amount. But let's head back to main screen. It is time, everybody. Everybody's favorite time of the day. But reverse it. Make sure small number, big number, small number. You might know. I just want to double check. Don't you get it wrong. Small number, big number. Go smaller number to bigger number. Always small number, big number. So it's I guess I see what you're doing. You're doing plus or minus. So you're doing the plus first. So it'll be minus plus. Points time, why not? What did you get on all the other parts of the question? We'll go take a quick look. Let me try to guess it. I'm going to guess this question. You ready? Is the independence assumption met? Yes. These are randomly selected, kind of. Are these the randomization condition met? Yes. Is this less than 10% of all flights? Yes. Is it nearly normal? Yes. This looks to be nearly normal, such that we have a large enough sample size. Passes the nearly normal condition. A lot to go on with the nearly normal large enough. We can be 90% confident the true proportion is contained, or the true mean of monthly flights missed on time, all that good stuff, is contained at the interval. 90% confidence interval. Going off of Tiffany's work right there, it looks to be about 0.54. What was your standard deviation, Tiffany? Can you tell me your standard deviation real quick? Because I think I can solve it. If you tell me your standard deviation, Tiffany, I think I can figure out the answer to this question. So just tell me your standard deviation, and then I'm going to guess my answer real quick. I mean, I guess I could solve it, but what fun is that? So if Tiffany tells me her standard deviation... Oh, that's the mean. Your mean was that. What's your standard deviation? What's your standard deviation? Standard deviation would be... The value of S right here is standard deviation. 2.77. Mine's smaller. So mine's a little bit smaller. That's right. So that's going to be that. 80 point... 79.82. Do we get it? Oh, no. Right there. Oh, we got one of them right. You gotta be kidding me. We got one right? That's the one we got right. We're right there on it. Really? How we get that one right? Let me see this. 80 point... Don't work problems like this. So I went back towards the middle, 0.3. 0.03. Back towards the middle. Oh, wrong way. There we go. There we go. Yep, they're all met. Don't be like Brian. Solve the problem right way. We take the margin, the standard error. Standard error. We take the sample size. We worked this out earlier. Check out the earlier part of the problem. There's that. And we divide the standard deviation by that. We multiply it by the t-statistic of 1.667. Oh, no. Yeah, that's correct. And that's the margin of error. And then we take this right here, and we go 80.2917 plus this, and there's the upper number. Oh, it gives a little leeway on that. And then we go 80.2917 minus, and it gave some leeway. Yep. So it's got a little plus or minus in it. Good stuff. Good stuff. And do remember we worked this out earlier. If you're watching the very end of this video right here, we did work it out, showing where t-statistics come from. This is a different version of it. A little bit of advanced right here. We haven't gotten to this yet, but check it out. Practice it up. We'll head back to the main screen. With that, everybody, we'll end off here. I'm going to go grab a quick snack before class. I would play this song 10 times. I'm going to get some new music this weekend too, maybe. I will see everybody later. Great work, Tiffany. Keep it up. Keep practicing. Keep reviewing. Test is next week. We're having a meeting tonight to talk about it. With that, I'll see everyone later. Bye for now, everyone. Bye. Kahoot coming up this weekend. Swing back for the Kahoot. Bye. Kahoot. Who will win the Kahoot? I hope you. Who knows?